Hey everyone, and welcome back to The Explainer. Today we are unpacking a really fascinating piece of research about an elegant new system called Belayer. As our AI systems get more and more advanced, training them is getting incredibly expensive. It takes way more time and it runs a massive risk of catastrophic crashes. While Belayer is designed specifically to act as a safety net for all of this, essentially saving massive amounts of compute and time in AI training.
All right, let's just dive right in. To really grasp why Belayer is such a game changer, we first have to understand exactly what it's trying to protect: Agentic RL. See, modern large language models, or LLMs, are no longer just passive text generators answering your questions in a little chat window. They're evolving into active agents. Through agentic reinforcement learning, these LLMs are actually being trained to use tools, execute computer commands, and modify files inside these long-horizon sandboxed environments. They are literally manipulating a persistent universe, and that completely shifts how they have to be trained and, more importantly for us today, how they can break. I want you to picture this for a second. What actually happens when an AI agent just forgets its entire universe mid-task? Imagine the sheer chaos and the massive amount of lost time when a long-running system crashes right in the exact middle of a complex, multi-step trajectory. If an agent has spent 10 minutes coding a website in a sandbox and the training engine just take ups, does that code still exist? Does the AI even remember writing it? This fragile in-between state is the massive bottleneck of modern AI training.
So here is our roadmap for today's explainer. We're going to start with the agentic AI shift, then look at the incredibly high cost of these system failures. From there, we'll introduce Belayer itself, and we'll break down its two-pronged solution: shadow workers and hidden environment checkpoints. Finally, we'll look at the actual results this system is pushing out.
Okay, part 1, the agentic AI shift, moving beyond text.
The absolutely crucial point here is that a single training trajectory now spans many rounds of back and forth between the AI thinking, generating tokens, and the environment actually executing those actions. Because of this, the semantic state of the training run is split right down the middle. It lives inside the LLM's context memory, and it lives inside the local file system of the sandbox. And doing this takes a shockingly long time. The median trajectory time is 460.8 seconds. Actually, let's put that into perspective. That is almost 8 whole minutes for just a single run. That represents a massive investment of compute time that is just incredibly vulnerable to being interrupted.
Which brings us to part 2, the high cost of failure and fragility at scale.
To really illustrate the severity of this problem, let's talk about tracking the validation success rate over 80 training steps. If you have a perfectly clean run with absolutely no faults, the success rate climbs steadily, eventually hitting over 70%. But what happens if you introduce a tiny, minuscule 0.5% failure injection? The success rate completely drops off a cliff compared to the clean run. Because these trajectories take so long to finish, even tiny, seemingly insignificant failure rates start compounding over the course of those 80 steps, and they will absolutely destroy your training success.
All right, moving to section 3, Belayer, the safety net. And this is a dual-layered solution.
To truly understand what Belayer is doing, we have to contrast the two major bottlenecks it's built to solve. On one hand, you've got rollout failures. This is when the inference engine itself crashes. The main cost here is lost compute. You're basically wasting highly valuable time restarting these massive GPU models. But on the other hand, you have environment failures. That's when the sandbox crashes. And honestly, this is way worse than just lost time. This is a corrupted reality. If the agent's file system breaks but its memory keeps chugging along, the entire training sample is ruined. So Belayer has two completely distinct recovery mechanisms to tackle these two distinct problems.
Before we get into those solutions, though, let's briefly map out Belayer's overall system architecture. The core idea here is isolation, keeping components separate to prevent a single point of catastrophic failure. We have the data buffer handling the prompts and trajectories. Then, the heavy lifting is completely split up. The rollout cluster conducts the LLM thinking, while a totally separate environment cluster handles the sandbox interactions. The training cluster optimizes the overall policy, and finally, the control module sits on top to orchestrate the whole shebang. Isolating that rollout engine from the environment execution is really the foundational step to securing the whole system.
Let's look at section 4, shadow workers save rollouts, focusing on faster engine recovery. Now, Belayer handles GPU memory in a really fascinating way. Think about traditional recovery. When a worker fails, you're forced to completely wipe the GPU and reload massive gigabytes of data. It takes forever. Belayer introduces something called a selective GPU state reuse protocol. The researchers actually audited thousands of real-world failure reports, and they realized something huge. When a worker crashes, the actual AI model weights and the raw KV cache arena, which are the absolute heaviest parts of memory, are usually perfectly fine. So, Belayer brilliantly separates those reusable heavy weights from the volatile worker process. If a worker crashes, the GPU simply holds on to the heavy weights, keeping them ready for a backup worker to instantly plug right back into.
This setup creates a completely seamless 5-step handover. We have a pre-initialized shadow marker just waiting in the wings. First up, the shadow detects that the main worker has failed. Second, it does a super quick health check on the GPU and flushes the cache, just to ensure no corrupted data sneaks its way through. Third, it remaps its memory buffers right back to those heavy weights we just talked about. Fourth, the router sends all the new requests over to the shadow. And fifth, it resumes training. By breaking it down into these 5 precise steps and reusing that heavy GPU state, the shadow worker can literally take over in less than 1 single second.
Now, you might be thinking, hold on, doesn't flushing that cache completely kill the performance? Well, if we look at the performance cost of a reprefill during a failure, the drop is actually incredibly minimal. Under a totally normal workload with 0 faults, the system processes 8,295 tokens per second. If you force a reprefill during a failure, it still processes 8,083 tokens per second. That drop is basically a rounding error, and it stays minimal across normal, long, and short inputs. The performance cost is so tiny it makes this protocol incredibly efficient.
All right, on to Section 5, hiding environment checkpoints, aligning memory and reality.
So the researchers call their ultimate goal here prefix consistency. Basically, this means ensuring that the recovered file system state, the runtime state, and the LLM's context all correspond to the exact same moment in time. Think of it like a video game save. You can't load a saved game where the final boss is already defeated if your character's memory doesn't remember fighting it. They have to be perfectly aligned. But pausing the training every few seconds to save the environment state would be ridiculously slow. So how do they solve this? When we look at how these trajectories play out, there are 2 main phases. The time the LLM spends generating a response, essentially thinking, and the time spent actually executing the action in the environment. Belayer opportunistically hides the sandbox backups entirely inside that thinking time. While the AI is busy generating tokens, the system quietly saves the environment in the background. And the data shows exactly why this is so brilliant. The median time spent just waiting for the LLM to think is nearly 437 seconds. The median time spent actually executing the environment action, barely 6.3 seconds. There is just this massive amount of natural wait time available to hide these environment backups, adding literally 0 latency to the critical path.
Finally, Section 6, faster recovery, better AI. Let's look at the actual results.
The performance gains here are, frankly, massive. By keeping those heavy GPU weights resident, Belayer achieves up to a 42 times worker recovery speedup compared to a traditional cold start. We are talking seconds instead of minutes. On top of that, environment recovery is 1.5 to 3.5 times faster, all while maintaining completely low overhead when no failures are happening. But perhaps most importantly, it completely eliminates those corrupted trajectory prefixes that completely ruin training datasets. It drastically speeds up recovery times, saving an immense amount of money and compute power.
So we've seen how Belayer removes the intense fragility from training AI agents in persistent worlds. Which leaves me with this final thought for you. With the massive, expensive bottlenecks of agentic training finally solved and these training environments finally locked down and secure, just how complex are the next generation of AI universes going to become? Thank you so much for joining me for this explainer. Keep learning, and I'll see you next time.